Hello everyone, my name is Yin Liu. I'm from Virginia Tech. Today I'm going to talk about my SecureCom paper, HTPD, Secure and Flexible Message-Based Communication for Mobile Apps. First of all, let me introduce a little bit about message-based communication in Android. You may know that in Android, apps exchange data via a special object, intent. Basically, source app put data into an intent, and the Android Intercomponent Communication, or ICC for short, will deliver the intent to the destination app. And there are two types of intent. For the explicit intent, only specific destinations can receive data. For implicit intent, any destination that registers a certain intent filter can receive data. To dispatch intents, Android provides start activity, which launches the activity the user interacts with, and send broadcast, which launches the broadcast receiver that processes broadcast intents. Well, Android ICC is useful and effective for enabling apps to exchange data. However, such scheme suffers from several security attacks. Let's look at three typical data leakage attacks. First, interception. That is, source app S wants to send its data to destination app D, but a untrusted app U intercepts this process and obtains the data. Second, eavesdropping. That is, S broadcasts its data to several apps through implicit intent. However, a untrusted app U also received this data. Third, permission escalation. Actually, Android provides a permission scheme to protect some sensitive information from being obtained unauthorizedly. For example, if you use Android phone, you must have seen such kind of notification that asks you to allow an app to access your location. If you click allow, then this app can obtain your GPS information, otherwise it cannot. So what permission escalation attack does is that the source app S has a specific permission, for example, GPS permission, so it can access GPS information. But the destination app D doesn't have such permission. If S sends GPS information to D, that means D's permission got escalated. So actually, we want to defend against these three attacks. There are several prior studies on how to eliminate these attacks, which can be categorized into two types. First, tent message data to track and analyze its data flow. FlowDroid and TentDroid can be used to do that. Second, we can track call chains of the source and destination apps. However, these solutions blocks all suspicious destinations. In other words, if it finds a untrusted data flow or call chain, all the involved destination apps will be blocked. Let's think about that. Untrusted does not equal to malicious, right? And this solution actually blocks all untrusted but not malicious app to get the delivered data. Our approach aims to not only defend against the three data leakage attacks I mentioned earlier, but also to enable untrusted but not malicious apps to securely access the received data. To that end, we apply homomorphic encryption and convergent encryption. Actually, our work is the first application of homomorphic encryption and convergent encryption to mobile middleware. Thus, our work balance the security and the usability in the data communication. So we provide HTPD, a novel model that strengthens the security of message-based communication via hidden transmission and polymorphic delivery. We also provide PolicyC, a reunification of HTPD that plug-in replace Android ICC, mitigating interception, eavesdropping, and permission escalation attacks. The most important is that by applying homomorphic encryption and convergent encryption, our solution allows untrusted but not malicious apps to operate on exchanged data. Here is HTPD model. HTPD stands for Hidden Transmission and Polymorphic Delivery. Let's first look at it. Say the source wants to send a message to the destination. So here is the original message. At the sending point, we first add some extra information to the original message, for example, the permission and routing information. Then we serialize it and encrypt the whole message. After that, we put this encrypted message into a wrapper message, so it becomes a transmission message. Because we hide the original message into the transmission message, we call it hidden transmission. Next, the transmission message will be routed to the destination. At the receiving point, we extract the original message from the transmission message, and we do the trustworthiness examination by using the added information. Based on the destination's trustworthiness, we choose whether or not return raw data, encrypted data, or no data. Because of this polymorphic behavior, we call the message polymorphic message and the delivery process as polymorphic delivery. Well, this is our model, and we implement this model in Android as a middleware called PolicyC. PolicyC basically follows several design choices that we made by consulting prior studies. First, it protects intent from leakage. Why we focus on intent? Because prior study shows that Android apps commonly store data in intent's extended data field. Second, it supports operating on encrypted strings and integer values. Why integer and string? Because prior study shows that Android API methods that manipulate integer and string values are among the top 10 mostly used. And finally, it supports start activity and send broadcast. Why activity and broadcast? Because one, the prior finding shows that start activity method is the most frequently used. Further, the data flow of broadcast allows multiple destination apps, so it supports the send broadcast to demonstrate HTPD's applicability. Here is the overview of the PolicyC. As I mentioned earlier, in Android, the source app puts its data into intent. Then the intent will be routed by ICC and delivered to the destination app. PolicyC did more than the standard ICC. First, we intercept the intent at source app's sending point and redirect the intent to our PolicyC. Then we encrypted the intent object and put it into a host intent as its data field. Then we send it back to the sending point. The Android ICC will route the host intent to destination app. At the receiving point of the destination app, we intercept it again and extract the original intent and transform it to polymorphic intent because it has polymorphic behavior. If the destination app is trusted, it will return raw data. If the destination is untrusted, it will return homomorphically or convergently encrypted data. So although the untrusted receiver cannot access the raw data, it can still partially use it. If the destination is malware, it will return no data. Let's look at an example. Say if an untrusted app gets the intent in point 3, it gets the host intent and cannot access the encrypted original intent. If it gets the intent in receiving point, it gets the polymorphic intent. Since the app is untrusted, it can only get the homomorphically or convergently encrypted data. PolicyC uses Android app permission and the relationship between the permission sets of the source and destination apps to measure the trustworthiness. That is, if the destination has fewer permissions than the source app, then we consider it is untrusted. Otherwise, it is trusted. And if the destination tampered with the data or intends routing information, we think it is malware. Let's look at our permission policies. We use Android permission set of source and destination apps to determine whether or not return encrypted data. Here is the encryption and decryption policies. The letter I represents intent and IEN represent encrypted intent. S is source app and D is destination app. The error means S sends intent to D at time t. This policy means if the permission set of destination D contains that of source app S, then we will return intent without encryption, otherwise the intent with encrypted data. Here is the permission transitivity rule. If S first sends an intent to D1 at time t, then D1 sends the intent to D2 at time t plus 1. In this case, if permission set of D2 contains the union set of S and D1, then we will return intent without encryption, otherwise encrypt the data. To implement PolicyC, we use several techniques. We use Android permission scheme to determine apps' trustworthiness, and use homomorphic encryption and convergent encryption to enable operations on encrypted data. Finally, we use Xpost to hook data sending and receiving point to enforce PolicyC's behaviors. Now let me introduce our evaluation. We have three evaluation questions. First, effectiveness. How effectively does PolicyC reduce the threats? Second, cost. What is the performance overhead of PolicyC on top of the Android SEC? Third, effort. How much additional programming effort is required to use PolicyC instead of Android SEC? We evaluate PolicyC on Nexus 6, Moto X, and Moto G2 with Android Nougat and Lollipop. And these Android releases are the most widely used version when we conduct this research. Here is our evaluation result. We mimicked 4 attack scenarios to check PolicyC's effectiveness, including interception at receiving point, interception before receiving point, eavesdropping, and permission escalation. For all of these cases, if the destination has insufficient permissions or tampered with the routing information, then the destination app cannot access the raw data. So PolicyC successfully defends against such attacks. We also did a case study by using 3 real-world Android apps: My Location, which can get users' GPS information; QKSMS, which can send short message; Intent Intercept, which can intercept implicit intent from other apps. We use My Location as the source app and the rest of 2 apps as untrusted destination app. Since My Location has GPS permissions, we use it to send implicit intent and explicit intent with GPS information to these destinations. We found that if these 2 destination apps did not have GPS permissions, that means their permission set is insufficient. So PolicyC will treat them as untrusted apps and return polymorphic intent with encrypted data. Now, if the user grants the GPS permission to these apps, that means user thinks they are trusted for getting GPS. Then next time they will get intent with raw GPS data from My Location. So our approach works. Interception, eavesdropping, and permission escalation attacks are mitigated. Here is PolicyC's overheads. Compared with Android SEC, PolicyC only adds about 40 milliseconds for start activity and send broadcast, and it has small energy consumption. And this is PolicyC's extra programming effort, which measures how many lines of code a developer needs to add for using PolicyC. It turns out applying PolicyC to existing apps, developers don't need to add lots of code, actually 4 lines of code at most. Okay, that's it. Thank you so much for your attention. For more details, please read our paper. I will be happy to take questions. Thank you.